Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to just go through kind of a quick demonstration here of how to apply the work energy theorem. So in this example, imagine we have this biker, and at the instant shown the biker is moving at 3 meters per second. The biker then rolls down this hill, dropping in elevation by 10 meters, and what we're going to do is try to calculate their speed at the bottom of the hill. Now there's a couple important assumptions that we need to work into this problem here. Assumption number one is that the biker's not going to be pedaling, meaning that the biker's not going to try to accelerate the bike during this time frame with her legs, because if she did, that would be an external work term that would need to be taken into account. So we're just going to imagine she coasts down this hill. Second, we're going to assume that air drag is not a relevant, not going to be an important force for this problem, because if it were, we would have to include an air drag force in our work term. All right. So as far as how do I apply to work energy theorem? So the first thing we do is we always label the two positions here. So I'm going to call this position 1 and down here position 2. Right? I like to make sure velocity vectors are drawn at both positions. So here at position 1, the velocity points to the right. I'm going to call that V1. Here at position 2, the velocity also points to the right. I'm going to call that V2. You notice I made the velocity vector larger. That's because just by observation here, I'm sure that the person's going to have a higher speed at position 2. Okay. Now I'm going to go ahead and write out the work energy theorem, which says PE1 plus KE1 plus work equals PE2 plus KE2. And we're just going to go through it term by term. All right, potential energies. Whenever you're dealing with potential energies, you have to decide where to measure those from, right? And what we call that is the datum. The datum is the location where we're measuring potential energy from. So I'm going to go ahead and put a datum in this problem. Because it's gravitational potential energies, the datum is horizontal. I'm going to draw this in blue. So there is my datum for this problem. So what the datum means is anytime our system is above the blue line, we would say its potential energy is positive. When it's at the blue line, we would say its potential energy is 0. And if it were down below the datum somehow, we would say it has a negative potential energy, which is perfectly fine. Now I'm just going to go through and do this term by term. All right, so the PE1 term we can write as mgh, where the h is going to be that height, and this potential energy is positive based on where I put my datum. Right. KE1, so kinetic energy terms are 1/2 mv squared terms, so 1/2 mv squared, but we have two different speeds. We have a speed at 1 and a speed at 2. So we can't really just put v here because we've got another v coming down the road, so I'm going to put a 1 on that, a subscript, to denote that as v1. All right, I'm going to leave a little space if you're following or taking notes. Leave a little space for the work term. I'm going to talk about that last. All right, the PE2 term. When the person is at position 2, they're at our datum, so the potential energy is 0. And then the KE2 term is 1/2 m v2 squared. All right. Now the work term. Let's go back and talk about that work term here. When you're dealing with work terms, you always have to, consider all forces acting in the problem. And a free body would be a good thing to do here. I'm going to go ahead and grab me another bike and move it and rotate it. Now what I'm doing is I'm putting this bike kind of at an arbitrary location in the problem. And now what we're going to do is consider all the forces acting on that bike. So if I were to draw a free body diagram of that bike at the location shown, the first thing that comes to mind here is we've got a gravitational force down. So in my free body, whoops, I may draw that something like that, right? And then label it mg. Another force to consider, we have contacts at the tires here, like here and here. So we're going to have forces for those. So there's going to be a pair of forces. Those are examples of forces that we would typically call normal forces. It's very common usually to take the pair of forces like that and then just group them into one force. So I'm going to represent those with one force vector this way. Whoops, except I like to draw my forces in black. I'm going to draw that with one force vector in this direction. That's going to represent my normal force. And again, that force vector is representing the forces applied to the system here and here. Now, if we were going to put air drag in this force, that would, or in this problem, that might go something like this. But in this problem, we're going to assume that air drag is a small force. If the person applied the brakes or something, that would apply a force this way, a frictional force. But again, we're going to assume she's going to roll down the hill. If she started pedaling and started like pumping the pedals really hard, we would then have to put a frictional force in this direction. But again, we're going to assume that away. So these are the only two forces acting on our system here. Now, work is force times distance, but only forces in the direction of motion do work. So when I look at this, the two forces, I consider them, and I ask myself, is this force doing work, the gravitational force? The answer is yes, because as we move from 1 to 2, there is a displacement in the direction of the gravitational force. But we have already taken that into account with a potential energy term. Right? We could have, if we wanted to, just ignored the potential energy terms like we've never even heard of them and put the mgh, force times distance, under a work term. And it would have been positive because the mg is in the same direction as the vertical displacement. Typically, though, we try to take those into account, gravitational forces into account with potential energies. The normal force doesn't do any work in this problem because the normal force makes a right angle to the direction of motion. So both forces have been considered, and we've decided to take gravity into account with a potential energy term, and the normal isn't doing any work, so we'll go ahead and put 0. All right. We kind of inspect this equation here, and we can see that we have a mass in every term. This will divide out. The mass doesn't divide out of every single equation, but a lot of them it does. So our work energy theorem here boils down to the following equation. I'm going to go ahead and put numbers in this. I'm going to put a little NCU for note consistent units. So under this term right here, we would put 9.8 times 10 plus, okay, V1 squared over 2 is going to be 3 squared over 2, and then equals V2 squared over 2. I'm going to go ahead and just solve that for V2 and leave the exercise, or the algebra, as an exercise to the reader here. So we're going to have that plus 9 halves times 2 square rooted. Okay, and what I get 14.3 out of that. That's probably a little fast for a bike maybe, but again, this is just an example. I'm sure she'll survive. So it looks like the speed at the bottom, again, about 14.3 meters per second. I think this, is a reasonable example of how to apply work energy theorem. You got to take into account potential and kinetic energies at both locations. I hope this video helps. Have a great day.